confidence intervals and confidence levels for sample proportions. To introduce this, suppose that we're interested in a 90% confidence interval. Consider a standard normal variable to begin with. So we've looked at that in the last few examples, and we should have a reasonably good understanding. So 90% confidence interval means that the shaded area here is 90%, and because it's symmetric, that means that we have 5% down each of the tails. If we look at the value marked Z on the axis, 95% of the area is below this, made up of our confidence interval and the 5% in the left-hand tail. We can find the value of Z using InfNorm or using the activity as we've seen in the previous examples. So the panels here just go through finding that value. And so if we call this 1.645, that means this is 1.645. And because it's symmetric, this one is negative 1.645. Remember, for the standard normal, the mean is 0. So we can see that the Z value is approximately 1.645. As the standard normal is symmetric about 0, the symmetric value to the left of the mean, such that 5% of the area is below, is negative 1.645, as we just said. We know that we can find the equivalent values for non-standard uniform distributions by multiplying the Z value by the standard deviation and then adding the mean. So the basic idea here is that if this is the standard normal with a mean at 0, and then over here we had some other normal with the same sort of bell shape, but you'll notice it's more spread out, less of a peak here, and that means it has a bigger standard deviation. So we'll say the mean for that one is mu, and the standard deviation is sigma, whereas over here the mean is 0, and we know the standard deviation is 1. If we multiply by the standard deviation, that changes the shape, and then adding the mean moves the location. So that's how we can transform from standard normal to any other normal. Now, let's say for a sample proportion that this mean is at p hat. And we already looked in previous examples of the fact that p hat is normally distributed with a mean p hat, and the variance for that would be p hat 1 minus p hat over n, and therefore the standard deviation for p hat is the square root of p hat 1 minus p hat on n. So if we have a 90% confidence interval for a sample proportion p hat, then we have p hat take away 1.645, which is the Z value for a 90% confidence interval as discussed above. And on the other end, we have p hat plus 1.645 times the standard deviation that we just talked about over here. So that is transforming it so that a 90% confidence interval here is now a 90% confidence interval over here. For a general confidence interval, we just need to find the appropriate value of Z for that confidence. For example, we've seen before for a 95% confidence interval that the Z value is 1.96. The quantity Z times the standard deviation is the margin of error. If you think about it, p hat is in the middle, and then we go up by the Z times the standard deviation, and we go down by Z times the standard deviation. So Z times the standard deviation, that is the margin of error.